Okay, so okay, I got my mistake. It's dr by dt, and it's minus 1 over u square du by d theta. It's L u square upon mu. I'm sorry, I'm terribly making this mistake. I made the same mistake in the notes. Please correct it. See, I have the notation inconsistency. I can't keep with the notation that looks similar. So it's kind of my backlog, but by simplifying, we get this equation. Perfect. Now I can get acceleration term so that I can substitute over here. Dun, dun. Right? Let me do it. It's nothing. It just take one time differential dr by dt, and we get d theta. I'm manipulating it. The art of manipulation. This is the art of manipulation. Let me tell you what I did. I divides d theta multiplied and divided by the same differential, and I took this dt over here so that I can use d theta by dt in this equation, and I will have theta. Right now my r dot, this is my r dot, say, will be a function of d theta, and because it's in differential form. Exactly. Now as I found my equation, which is, see why I did it, because we have d theta term, so it gives me a complete ideology, a complete hint to say that I have to use this to get this. So it's just a pure manipulation so that I can use this term around here without any hindrance. So it's du d theta L by mu d theta by dt. So I'm going to get very simple, decent, small differential equation. T square, which is equal to minus t square u upon d theta square upon L square u square upon mu square. So yeah, it looks cute, it's look beautiful. What I have to do is I just have to substitute this term, the star term that we did it. This is our star term. Take a moment to see this equation. Alright, so further I'm going to substitute this particular equation that we just got to the star equation. That's easy, and we will get, so okay, I'm also going to resubstitute my r dependency, so I'll get a complete equation, theta square u square L square mu, which is L square mu u cube. Okay, we have potential term in the form of the u. Okay. Okay, that's good. Also the L square, and here we have L square. And here we will have, okay, have mu. So okay, this is just my rough work. I'm just doing it for myself. You can see the final equation would be in this form: L square. So let me rewrite this equation nicely, because I have to explain few terms regarding this equation, differential equation. Now, this is an equation of SHO family. That means it is an equation of SHO family with an additional constant term, right? When I talk about SHO, it means simple harmonic motion, alright? This is an equation of that particular family. So, and if you see this, it's not it's a second order differential equation, but also it is not homogeneous. It consists of two parts. What are the two parts? I hope this works. The solution consists of two parts. One, which is the angular independent, let's add angle independent, and then solution, which is u naught equal to mu, this is mu g m1 m2 upon L square. This particular term mu g m1 m2 upon L square is equal to u naught, which is an inhomogeneous also I'm going to write circular orbit in bracket, which I further explain to you. Now if you see this equation, this is a beautiful equation. Now the second is the sinusoidal dependent term, which is an homogeneous equation and which is characterized by a constant which we call amplitude. Right, this is what an SHO equation of a family looks like. So A and theta naught, A and theta dot are constants that are yet to be determined by the forms of the orbit, the geometrical forms of the orbit. And also one more thing, important thing is 1 upon u naught, which is r naught, is equal to it defines what we earlier defined as semi-lattice vector. Now you see why I defined it as semi-lattice vector earlier. I hope you do. If not, wait for it, because we are currently going to study for the orbit, so it's kind of interesting. Now, as I told you, it's a second order inhomogeneous differential equation. That means the general solution consists of two parts. General solution consists of two parts. Homogeneous and inhomogeneous equation. So what we get is 1 upon r naught 1 plus r naught a theta minus theta dot. Now you can see we are getting to that equation. R naught, just rearranging it, theta minus theta dot. Now I define this quantity as my epsilon, and theta naught, I'll set the theta naught, which is constant, and I have absolute freedom to set it to whatever I want, so I'll choose pi. Voila, we got the equation that we set to find that we did the same equation that we found by the first method. It was far easier this time, as you can see, but the easiness, because we didn't have the easiness, came from the manipulations of the differential equation, correct? See here, the manipulations over here, right? The manipulations of the differential equations over here. For this you need to be extremely smart about it, and the traditional way doesn't offer you this, but it was because of the traditional way we got this equation from the first method, the traditional way, After that, we realized that it can be manipulated to a certain extent to get a same equation in a much easier way, rather than dealing with the, oh my god, the integrals, I mean the terms which are scary to look at. So we have completed the first and the second method. We got the equation. Now I'm going to proceed in the same video, in the same lecture, what to do with this result. Basically, see, we have two constants of motion, L and E. We have this equation in terms of R naught and epsilon. We do have this, so let me state it. This is mu, alright. Epsilon square minus 1 upon 2 R naught. So now these are my two constants of motion, alright. Now my R as a function of theta is R naught upon 1 plus epsilon cos theta. See this equation. This particular equation is the equation of a general conic section. Right, exactly. Now you can see why I defined it as semi-lattice rectum. See, it was because the epsilon and R naught are the part of conic section. You need to have a strong background in a conic section. So I can readily show it to you in the Cartesian form, which doesn't take much longer. So x is R cos theta and y is equal to R sin theta. That's exactly how we proceed in terms of converting the coordinates to the Cartesian equation, and we do R naught plus epsilon cos theta, epsilon R cos theta. Then we square them individually to get and square root, so we can get a 2. So then we can just square plus y square and state it as R naught square plus 2 epsilon R naught x plus epsilon square x square. Now I'm just going to rearrange this particular equation. Alright, I'm going to rearrange this equation into it. X square 1 minus epsilon square format. 2 epsilon x R naught plus y square, which is equal to R naught square. Now this is the general expression of a conic section, but it is a particular kind of conic, a general equation of conic section, which is along the x-axis. Now for a given R naught corresponding to a non-zero angular momentum, this is very important, I want you to listen carefully. For a given corresponding to a non-zero angular momentum, R naught corresponding to a non-zero angular momentum, there are 4 cases. 4 cases determined by the value of eccentricity. Determined by value of eccentricity. So let's see the 4 conditions. I'll just briefly state. So if I state briefly, we can look at them in detail in the next video. So I'm just setting a base in this video. Okay. So first is when epsilon is equal to 0, there finds an energy which is lies between 0 and R is equal to R naught. At such type, and when we have this condition, our equation changes to x square plus y square is equal to r naught square, right? When epsilon is equal to 0, this goes away, x square, and this term vanishes. We have x square plus y square is equal to r naught square, which is exactly this equation. And if you recognize this is the equation of circle, right? Now let's do the second case when epsilon is okay, it is epsilon is between 0 and 1. So at such times my energy will be between energy minimum and 0. So, and what will happen? The generalized equation can be Ex. This is some kind of a generalized equation where A is greater than 0 and k is greater than 0. This is a generalized equation, just the generalization, because there is an inequality and it's kind of hard to see it. So now this equation, this particular equation with this condition defines a condition called ellipse. This is very important to study Kepler's laws. Change the page. Now the second condition, the third condition is when epsilon is equal to 1. Now this must imply the energy should be equal to 0, and from this particular equation I can easily get what it takes to write as y square upon 2 r naught minus r naught upon 2. As you can see, this equation, okay, there's a negative sign, there's a negative sign, this goes to this side, it picks a positive sign, and r naught comes over here, it picks a negative sign, so we have minus r naught upon 2 plus y square. So this whole term just comes down, so it gets multiplied with this equation, and it's beautiful to see how we get a simple equation, and this characterized, and it's the equation of parabola. It's also very important to look. When epsilon is greater than 1, the energy should also be greater than 0, and our general equation is characterized again by some kind of an equation, a generalized equation, where A should be greater than 0 this time, and it's the same condition, A should be greater than 0, K should be greater than 0, and this corresponds to an hyperbolic orbit. So when energy is greater than 0 and epsilon is greater than 1, we get this kind of hyperbolic orbits. So in the next lecture, I'm going to teach you about energy diagrams and what I call the effective potential energy, and the orbits, the results which are going to be expanded. The results of this lecture are going to be expanded. So we are going to see each orbit, the hyperbolic, parabolic, circular and elliptical, in detail. Then we will see, let's see it in the next video.